Hi guys, welcome to this set of videos. What we're going to do here in this set of videos is they're going to go along with the notes now where we're going to talk about the trigonometric ratios, sine, cosine, and tangent, that we just learned about in the previous sections and how those trig ratios relate to the sides of a couple of special triangles. So the first thing we're going to do, right, is talk about what are those special triangles. There's two of them, and we'll talk about what they are, and then how the trig ratios, sine, cosine, and tangent, relate to the side lengths, the lengths of the sides of those special triangles. So here we go, a couple of our learning target, what is our essential question? What is it that we're trying to do here in this set of videos? And it's simply this. We're asking, what do you know about the side lengths and the trigonometric ratios of special right triangles? So first we need to figure out what are the special right triangles, and then we'll talk about how the trig ratios relate to those special right triangles. In order to do that, first we're going to need to talk about how the trig ratios relate to the side lengths of those special right triangles. Okay, first, special right triangles. What does that mean? Well, here's what we've got. There are actually two special right triangles, what we call special right triangles. And a great question would be, well, what makes them so special? I'll get to that in a second, but essentially here's what they are. There are two of them. These special right triangles are the 45, 45, 90. So that's going to be a right triangle, right? 90 degrees means a right triangle, where the other two acute angles are 45 degrees and 45 degrees, right? 45 plus 45 is 90, 90 plus 90 sums to 180. So I know it's a triangle, the triangle sum theorem. So that's the first one. The second special right triangle is the 30, 60, 90 right triangle, right? So 90 degrees is what makes it a right triangle. That's a 90-degree angle. 30 plus 60 is also 90. 90 plus 90, 180. So those are our two special right triangles. Now, the ratio of the sides of these special right triangles is actually really, really important. And that's what I talk about right here. So I've given you both triangles. Here's the 45, 45, 90, right? 45, 45. Those are my two acute angles. And there's my right angle. In fact, let me go ahead and put my right angle symbol in there. Boom, there's my right angle. And then this is the 30, 60, 90 right angle, or right triangle. And again, the two acute angles, one of them is 30, the other acute angle is 60. Now again, why are these triangles special? I'll talk about that in just a second, but for now, really what's important is the ratio of the sides. It doesn't matter how big or how small these triangles are. In the 45, 45, 90 triangle, right, the ratio of the three sides, so this guy right here, the ratio of the three sides of this right triangle is 1 to 1 square root of 2. Here's all that means, right? This side, whatever the length of this side is also the length of this side, and then the hypotenuse, right, will be the square root of 2 multiplied by whatever the length of these two sides are, right? Please notice x, 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 right? X shows up all three sides, so whatever the value of x is, right? Let's say x is 2. Well, then this guy would have a length of 2. This guy would have a length of 2. What would be the length of this guy? 2 times the square root of 2, right? That is the ratio for the lengths of the sides in every single 45, 45, 90 degree triangle, right? Every single one. Doesn't matter how big, how small, whatever the length of this side is, it's congruent to this side. And then it's related to this side by simply multiplying whatever the lengths of these sides is by the square root of 2. Okay, the 30, 60, 90 triangle. Well, again, what we're really interested in here is the ratio for the lengths of the sides. So the ratio, the three sides of this right triangle are 1 to 2 to the square root of 3. Okay, here it is. If this guy is x, right, x, whatever x is, you can make it any number you want to. To find the length of the hypotenuse, you'd simply multiply x by 2. So this guy is twice as long as this guy, right? We use x equals 2 over here. Do the exact same thing. If x is 2, this guy is the length of 2, this guy will have a length of 4. It's twice as long, right? That's the ratio. And then to find the length of this third side, it'll be whatever x is multiplied by the square root of 3. In this case, 2 times the square root of 3. Again, it doesn't matter how big or how small you make the 30, 60, 90 triangle. The ratio of the sides is the same in every single 30, 60, 90 right triangle. All right, now, why are these ones so special? Why do we call these our special right triangles? Well, here's the reason why. Here's where they come from. So the 45, 45, 90 triangle comes from simply taking a square, right? I've got a square here, and we cut that square right on the diagonal. We divide it in half. That gets us a 45, 45, 90 right triangle. Again, where does this value come from then? Well, the length of the diagonal, right, would simply be, if I were to do the Pythagorean theorem, so a squared plus b squared equals c squared. Well, I've got my right triangle right here, right? So the lengths of the sides, are x and x. So that would be a and b. So I would have an x squared plus x squared is equal to c squared. Let's just say we hadn't already talked about this. We're trying to find the length of the hypotenuse, right? Because I know that the sides of a square are always the same. All 4 sides are the same. So whatever the length of this side is, the length of this side has to be as well. What we don't know is what's the length of the hypotenuse. Well, here's what I do. I go ahead and add those guys together and I get 2x squared equals c squared. Okay, no problem. Well, what I'm trying to do, right, is I'm trying to solve for c. So let me just swing this guy around a little bit. C squared is equal to 2x squared. We're going to take the square root of both sides, right? In order to get the c by itself, I have to get rid of the square. Well, I'll just take a square root of both sides, and here's what we wind up with. C is equal to, look at this, right? What happens when I take the square root of 2? Well, you get the square root of 2. What happens when I take the square root of an x squared? Well, the square and the square root cancel each other out, and I'm left with just an x. X square root of 2. So where does the value for the hypotenuse, the length of the hypotenuse, come from? It simply comes from doing Pythagorean theorem, right? The sides of the square is always the same, and then you just run that diagonal through there. Pythagorean theorem finds you the ratio for the length of that side. The other triangle was the 30, 60, 90 triangle. Why is that one so special? Well, the reason that one's special is because it comes from an equilateral triangle. Now remember, in an equilateral triangle, once again, the length of all 3 sides is exactly the same. What we're going to do, just like we did for the square, we cut it in half. We're going to take that equilateral triangle, cut it in half. We cut it in half. Now here's what happens, right? The length of each of the sides of an equilateral triangle are congruent. They're all exactly the same. So what happens to this side down here when I cut it in half? Well, yeah, if the length of each of the sides was 2x or 2a, in fact, since up above I called them x, go ahead and throw x's in there, 2x, 2x. Well, if the length of this side is 2x, when I cut it in half, each of these guys would be x and x. Well, no problem now. Again, Pythagorean theorem. The length of this side is 2x. The length of this side is x. I'm trying to find this missing piece, that missing leg, and Pythagorean theorem will do it for us. A squared. If it'll work, a squared plus b squared is equal to c squared. Careful, this time around, x is the length of a leg. 2x is the length of the hypotenuse. So I will have an x squared plus b squared is equal to 2x squared. And here we go, we're going to solve for b. So b squared is equal to, all right, 2 squared is 4. X squared is an x squared, and I will subtract this x squared to the other side. That means that b squared is equal to 3x squared, right? If I have 4x squareds and I subtract 1, I'm left with 3x squareds. Well, now I gotta solve for b. Well, that means I have to take the square root of both sides. Take the square root of both sides. That gets the b all by itself. Sorry. That gets the b all by itself. And then here's what happens. Square root of 3. Well, there's nothing I can do with that. I'm just left with the square root of 3. But when I take the square root of an x squared, I'm left with an x. And look at that. That's exactly what we've got here for the length of this side. The ratio for the length of this side would be x times the square root of 3. So those are two special right triangles, 45, 45, 90, and then the 30, 60, 90 triangle. And these ratios right here are really important. For the 45, 45, 90, it's 1 to 1 to the square root of 2. That's the ratio of the lengths of the sides. And then the 30, 60, 90, 1 to 2 to the square root of 3. And again, if you ever forget, Pythagorean theorem will help you out. Head on over to the next page of the notes. We'll take a look at solving some problems using these ratios for our special right triangles. I'll meet you guys there.